Okay, so in this particular lesson, we are going to look at part two of limits. Part two of that's proving basic theorems. Proving basic theorems. Okay, so before we continue, I'm going to introduce you to a certain rule, a famous rule under limits, and that rule is called the L'Hopital's rule. So the rule is called the L'Hopital's rule. Now, what does this L'Hopital's rule state? So the L'Hopital's rule states that if you have a function, f of x, and you have another function g of x. So if you have f of x and you have g of x, and they are dividing. So if you have f of x over g of x, right? Where where the f of x over the g of x is giving us 0 over 0, comma, a number, let's say a over 0, comma, let's say infinity over a number, infinity over infinity, then let's say a number b over infinity. So these are the basic concepts here that you're supposed to look at. So if f of x divided by g of x is giving us 0 over 0, a over 0, infinity over infinity, and b over infinity, we employ the L'Hopital's rule. So L'Hopital's rule is basically saying that if you have limits as x approaches a variable, let's say a, of f of x over g of x, and you are having these circumstances, what when you're having these circumstances, when you take the limits at a, and you are having these circumstances, when you take the limits at a, then what you are going to do is that you are going to, so this particular limit as x approaches a of f of x over g of x will be equal to limit as x approaches a of their derivatives. So the derivative of f of x over the derivative of g of x. Now this can continue. This can what? Continue. You can derive and derive and derive and derive. Right? You can do the derivatives like multiple times. So you can be getting limits as x approaches a of f of x, the second derivative of f of x, over the second derivative of g of x. So you can be getting things in this manner, right? So f of x, you can also go to a third derivative, fifth derivative, till you get none of these conditions in your approach, none of these conditions in your approach. So till you do this, you are going to keep on differentiating. Now, about the differentiation, is very important. Now, as you can see, you differentiate the functions separately. You don't differentiate them as a function using the quotient rule. So note note the quotient rule is not to be used. So the quotient rule is not to be used here. Why? Because these are all functions. We don't differentiate them as one function. We differentiate them as what? Separate functions, right? Separate functions. Okay. So now you've seen the L'Hopital's rule. Now we are going to do some examples before we continue. We're going to do some examples before we continue. So our first example is you have to find limit as x approaches 3 of 2x plus 1 all over x minus 3. So I have to find this limit. Now you can see that if I put 3 directly into this, I'll come and get 7 over 0, which is wrong, which should not what prevail. So what I'm going to do is that since I've gotten this condition, one of these conditions here. What I'm going to, I want to differentiate. So I differentiate. So limit as x approaches 3. So when I differentiate the top. So differential of 2x plus 1 is what? 2 over differential of x minus 3 is what? 1. So this will be equal to, so this will be entirely equal to just the 2. So the limit will be just 2. Because you don't have anything to substitute 3 there. You don't have any x to substitute the 3 there. That's why I just put the 2 there. Okay. Now let's take another condition. So a same question actually. But here we will have an x to substitute. So we have limit as x approaches 2 of x squared minus 4 over x minus 2. Now the derivative of this will be 2x over 1. 2x over 1. So we will take the limit as x approaches 2 of 2x. So limit as x approaches 2 of of the 2x. So of 2x, which will be equal to 2 into bracket 2, which will be equal to what? 4. So as you can see, which will be equal to what? 4. Okay. So then we've looked at some examples. Now let's look at a trig example. So we are solving 3 examples. So we've done 2 so far. So let's look at a trig example. So we are saying we should find limit as x approaches 0 of sine x all over, so sine squared x all over tan x. Now as I said, you can see sine 0, so sine squared x. So if I put sine 0 over tan 0, I'm going to get 0 over 0, which is a condition that we stated earlier that should be avoided. So hence you have to do our what? Differentiation. Now bear in mind that tan x is the same as sine x over cos what? X. So let's substitute this. So we come and get the limit as x approaches 0 of sine squared x over tan x to be equal to sine squared x times, I'm doing the reciprocation, so you come and get times cos x over sine what? X, times cos s over what? Sine x. Now this sine x will cancel 1, so you come and get sine of what? X, sine of x, which will be equal to sine x cos what? X, sine x cos x, sine x cos x. So you can see sine x cos x. Now after we've gotten sine x cos x, sine x cos s, now you can see if you substitute directly the 0 into it, you come and get, if you substitute directly the 0 into what you've gotten so far, substitute the 0 into it, we are going to get sine of 0 multiplying cos of 0, which will be equal to 0 times 1, which will be equal to what? 0. So this is our final answer. So we accept these values. There's entirely 0. That's why I didn't write 0 over a number, a variable, to show it's a number. So the answer is what? 0. So there's no need to do a differentiation of this. As long as you get a variable or you get a proper answer which is not infinity, you are already good to go. So as I said earlier on, we are going to prove some basic terms, some basic things you have to know under limits, some basic things you have to learn them. So let's start off with so we are going to start off with why. We're going to start off with why the limit. It's why limit as x approaches 0 of sine x over x equals 1. Now this is equal to 1 because of the L'Hopital's rule. It's equal to 1 because of the what? The L'Hopital's rule. Now, as you can see, if I put 0 into this, I'm going to get sine 0 over 0, which will be equal to 0 over 0, which must be what? Avoided. So hence the L'Hopital's rule come into play. So when I differentiate sine x, I'll come and get what? Cos x over what? 1. And cos 0 will be equal to what? 1. As you can see. So proved. So you can see. So L'Hopital's is basically the factor for doing these things. So if you take tan x2, limit as x approaches 0 of tan x over x equals 1. The same thing. You come and get tan of what? 0 over what? 0, which is not acceptable, which will give you 0 over 0, which is not acceptable. So when you differentiate tan x, you come and get what? Sec squared what? X. And sec squared, you come and get what? Sec squared what? X. That's the derivative of what? Tan x. The derivative of what? Tan x. Now we know that sec x is 1 over cos x. So we know that sec x is what? 1 over cos x. It's 1 over cos x. So this sec squared x is the same as 1 over cos squared x. And we're already doing that. So 1 over cos 0, which is cos 0 is what? 1. So 1 over 1 is still 1. So as you can see. So you just want to check. Now, we move on to an intriguing one. Taking limits as x approaches 0 of sine inverse of x over x. So we are going to prove this one too. Now, as you can see, it will be total infinity that we'll be looking at. So you have to differentiate this particular thing. You have to differentiate. So now we have to know the derivative. So if we differentiate x is 1, so we come and get the derivative of sine inverse of x. So the derivative of sine inverse of x, that's the first derivative, over 1. So the derivative of sine inverse of x over 1. Now what's the derivative of sine inverse of x? Now the derivative of sine inverse of x is equal to negative cos x sine to the power sine like this. So this is the derivative of what? Sine inverse of what? X, as it goes. Now you can see that if we still put 0 into this, we are not going to work things out. 0 because because the actual thing for this has been proven. It has been proven as limit as x approaches 0 of sine inverse of x over x is equal to 1. So this is the what? The proof. And we want to arrive at 1. If you put 0 into it, no, we are not getting. We are not getting because of this sine inverse of x. So you have to continue differentiating. So we look for the second derivative. So the second derivative of negative cos x sine inverse of x, the second derivative. So this is the first derivative. This is the second derivative. So the second derivative of this particular thing here, the second derivative of this particular thing here. So I'm starting with the cos side. So I come and get, so I'm doing product 2. I come and get sine x plus 2 cos squared x sine negative 3x. As you can see, now if I put still 0 in, no, it's on. So I now go to my third derivative. Now it's my third derivative. I'll come and get cos x plus, now this is the part that matters to you also. I'm just looking at getting cos x from it. Whilst I'm getting cos x, nothing, because you know that cos 0 is 1. The cos is the only thing that when it is cos 0 to give us 1, the rest it will give us 0. So we are just looking at 0 or infinity. So we are just looking at what? The cos x part. So we end here. because we are not learning how to do the differentiation here. So we end here. So quickly we substitute our what, our cos, our 0 into it, so making what, cos 0, and cos 0 is equal to 1. So as you can see, there, right, as you can see. So we are seeing that these are what, basic concepts of what, how things should be, what have been what proven. Now let's take one last example. Let's take one last, I'll give you a bonus example too. So let's take one last example. As I said, I'll give you a bonus example. Okay, so two examples, because I'm giving you a bonus example. So now we are saying that limit as x approaches 0 of sine x degrees over x is equal to 1. Now this is very simple. Now we know that limit as x approaches 0 of sine x over x is equal to 1. We know this already, right? From this, now they are saying this one is equal to 1. In other words, they are saying, so as I said, so sorry, this one is not equal to one other. It's equal to, this one is equal to pi over 180 degrees. Pi over 180 degrees, right? So as I said earlier on, pi regarded as what, 180 what degrees. So this particular thing is still equal to 1. It's just that because of the degrees, they are trying to make it in what, put the angle in radians. So I'm just going to get pi over 180 degrees, which is equal to 1. There's no big deal here. As simple as that. Now with my bonus question. Now I'm seeing that limit as x approaches 0 of e to the power lambda x minus 1 all over x is equals to 1. Sorry, is equal to lambda. It's equal to lambda. Now you can see, if I put 0 there, I'll come and get everything to be infinity. So I'll come and get 0 over 0, which I don't need 0 over 0, right? So you can see, as soon as I put 0 in here, I'll come and get e to the power 0 minus 1 over 0, which I don't want this. So I differentiate. So let's look for the derivative of e to the power lambda x. And the derivative of e to the power lambda x is lambda e to the power lambda what, x. Now if I put x to be equal to 0, I'll come and get lambda e to the power 0. And e to the power 0 is equal to what, 1. So I eventually come and get what, lambda. So as you can see, I eventually come and get what, lambda. So this is my final answer. It's our final answer. So this is actually the part 2. So in the part 3, you get to know the other theorems. And more, be solving more complex examples. So in the next part, you'll be getting to know other theorems and solving more complex examples. So watch out for the part 3 for the theorems and more complex examples. Okay.